Hey everyone, welcome to our first lesson on polynomials, which is Unit 1. And this lesson is going to deal with factors and multiples and just trying to get our mind kind of wrapped around what the definition of those guys are. I'm hoping that this note is going to feel very, very familiar to you. A lot of it comes directly from junior high. But we want to take a few lessons here as we get into polynomials, just to make sure we're all on the same page. Everybody's coming from a different grade 9 experience. Everybody had a different grade 9 teacher. And so we wanna make sure we're all in the same spot as we move forward, okay? So the best way to handle these video notes is to get super comfortable pausing me as well, okay? I might read through a question and then I'm gonna go directly answer it. Well, it's gonna look really easy if you just watch me answer it. It's a lot harder if you're trying it yourself first, and you'll learn a lot more though if you try it yourself first. So what I want to encourage you to do is always pause me, try the question, and then come back and see my explanation and see if what you did matches what I did. Okay. Okay, so a little warm-up problem here. I'm going to kind of skip over that, but you can try it at home if you like. I will show you the answer so you can pause me if you'd like to try it, okay? Now, what I would like you to do, and this is a spot where I'd like you to pause me, I want you to grab your textbook. Now, that may be available online. There's links on D2L for your textbook, or you may have a physical copy of your textbook, just depending on what your current situation is. We're looking at page 134 to 138. Part of my job as a teacher is I want you to learn the concepts, but I also want you to get some life skills on you know, how to handle textbooks and how to handle reading, not reading necessarily every word, but reading in order to try and glean information from it. So I'm going to tell you that I'm about to give you definitions for these 4 words or phrases. I'd like you to pause me, take a look at pages 134 to 138 in your textbook, and see if you can figure out some of those things before I give you the definitions, okay? All right, so here are the definitions. Factors. Factors are numbers that multiply together to obtain a product. Now, a product is the answer to a multiplication question, okay? So, for instance, 5 is a factor of 30 because 5 times 6 is 30. So, in that same breath, 6 is also a factor of 30, okay? When we take a number and we split it into a multiplication sentence, we are splitting the number into factors. So by taking 30 and splitting it into 5 times 6, I'm splitting it into 2 factors, 5 and 6, okay? A multiple is the product of a given number and a natural number. Natural numbers mean your counting numbers, so 1, 2, 3, 4, 5. So multiples of 5 would be all the numbers that you just count by 5s on. So 5, 10, 15, 20, 25, 30, 35, 40. Those are all multiples of 5, okay? Students get factors and multiples mixed up all the time. What you want to think about here is factors are always smaller than the original number that you were given, and multiples are always larger than the original number, because with multiples, you're taking the original number and multiplying it by something, okay? The one exception to that phrase is the number itself. The number itself is actually both a factor and a multiple, okay? But other than that, factors will always be smaller than the original number, and multiples will always be larger than the original number, okay? A prime number is a natural number that has 2 distinct factors, 1 and itself. Any number that's not prime is considered composite. So prime numbers are like 2, 3, 5, 7, 11. When I think about the factors of all those guys, I can only say that they're 1 and itself, okay? If I'm not prime, I'm composite with one exception, and that is the number 1. The number 1 is special like my mom told me I was. It's neither prime nor composite, okay? You can't call 1 prime because the definition of a prime number is that it has 2 distinct factors. 1 actually doesn't have 2 distinct factors, it only has 1 factor. So it's special. Okay, now prime factorization. Now this I'm hoping you're a little familiar with from junior high. Prime factorization refers to the breaking of a composite number into its prime factors. We would then write the original number as a product of prime numbers. Remember, the word product here means a multiplication, the answer to a multiplication sentence, okay? The least common multiple, also known as the LCM, is the smallest number that's divisible by two different numbers. It is the smallest multiple that both numbers share. With fractions, it's usually how you get your common denominator. And then the greatest common factor is the largest factor that two numbers share in common, okay? All right, so the first thing we're gonna practice is a little bit of factor trees. We're gonna do the prime factorization of 12. So what we do is we think, okay, I need two numbers that multiply together to give me 12. Maybe you thought of 2 and 6. Maybe you thought of 3 and 4, okay? Maybe you thought of 1 and 12. Forget about 1 and 12 if you did think about 1 and 12, because remember, we're trying to break this down into prime factors. 1 is not prime, and so I don't care about the 1, okay? So you can either choose 2 and 6, or you can choose 3 and 4. Totally doesn't matter. I happen to have chosen 3 and 4, but if you chose 2 and 6, it doesn't matter. You're still gonna get the same answer as me at the end, okay? Now you look at that and you say, okay, do I have a prime number here? Yes, I do. 3 is prime, okay? So you could just circle 3, just as a notion to you that, hey, that's prime, I'm done. I don't need to break that guy any further. But 4 is not prime. So now I want to say, okay, can I break 4 into another multiplication sentence? And I can do that. 4 is 2 times 2. Both 2 and 2 are prime. And so now I have broken 12 into a series of prime numbers that are being multiplied by each other. It would be 3 times 2 times 2. So 3 times 2 times 2 would give me 12, okay? So I can write it as 2 times 2 times 3, or I could write it, I could just group the 2's together, right? You'll remember from exponents last year, 2 times 2 could be written as 2 squared, okay? And it'd be better to group the similar ones together with one exponent. Now, by convention, we would always write this in order from smallest prime factor to largest prime factor as well. Okay, it's not that it's like totally wrong if you said 3 times 2 squared. That's still mathematically correct. But we like to do things in a way that it's a common communication amongst everybody, okay? Math is very much a language, and so we want to learn not only to speak the language, but to speak the language well. And it's little things like that that help us to speak it commonly. Okay, so you try 324 now. I walked you through the first one. I want you to pause me and try 324. So what I did is I broke 324 into 81 times 4. Now you may have just gone 2 times something, or you may have gone in so many different ways you could try this. You could have gone 9 times something. You could have gone 27 times something. It doesn't matter. Whatever you found, you just keep working with that, and you keep breaking each one down, down, down until you hit prime numbers. And when you hit prime numbers, you're done, okay? So I started with 81 times 4. Then I broke my 4 into 2 times 2, which was prime. I broke my 81 into 9 times 9. Then each 9 got broken down into 3 times 3. So altogether, I have 2 times 2 times 3 times 3 times 3 times 3. Or 2 squared times 3 to the 4. 2 squared times 3 to the 4 is how I would write that as a product of prime numbers, okay? Now, you can always check your work too, right? You can grab your calculator out and you can go 2 squared times 3 to the 4. For if you're a Casio or a TI, your exponent button is a button that looks like this, okay? If you are a maybe a scientific calculator that you have, it might look like that, or it might look like this, y to the x, or sometimes I've seen it as x to the y too, but those usually refer to your exponent buttons, okay? All right, good job, guys. Now let's try 3,920. So pause me, see what you can do. So I right away just saw, I started taking out 2. So I went 2 times 1960. And so that 2 is done. And then I went, okay, I'm gonna break the 1960 down into 2 times 980. That 2 is done. The 980 gets broken down into 2 times 490. So I'm just keeping keeping my 2's. I'm just taking 2's out each time until I can't take 2's out anymore. You don't have to do it this way. Some of you at the very beginning of this question may have looked at this 3,920 and said, hey, why don't I just take a 10 out right away because I see I divide by 0. Perfect, okay, doesn't matter. So my 490 gets broken down into 2 times 245. The 245 no longer can be divided by 2, but I can divide it by 5. So I'm going to go 5 times 49. And then the 49 gets broken down into 7 times 7. So the green that I'm showing you here is all of my prime factors. So I can write this as 2, take a look now. I've got 1, 2, 3, 4. So 2 to the 4 times 5 times 7 squared. 2 to the 4 times 5 times 7 squared. Okay, 2 to the 4 times 5 times 7 squared. I'm just going to hide my video for a sec because I think you can't see that. So that was my final statement there. Okay. All right. Next up, we're going to take a look at finding the greatest common factor. Now, there are 3 different ways I'm going to show you how to find the greatest common factor. 2 of them are algebraic. If I ask you to find the greatest common factor on a test, you need to show me work. You need to show me some sort of algebraic method. Okay, so that would be either method 1 or method 2. I will also show you, if you have a graphing calculator, whether it's a TI or a Casio, I will show you how to check your work on a TI or Casio. But again, if you just give me an answer, anything you ever do with me, if you just give me an answer, I never care about that. It's never worth anything. Even if it's right, it's not worth anything. You always want to have work to back your statements up. Okay, it all goes back to, it's a communication thing, right? You want your mathematics to be well communicated. So method number 1, I'm just going to list all the factors of 126, and I'm going to list all the factors of 144. Now, you got to think this through very carefully. When you want to do this, you want to make sure you go in order. That way you know you don't miss anything. So I'm going to start with 126. I'm going to go 1 times something. Then I'm going to go 2 times something. I'm going to go 3 times something, okay? And I'm going to keep doing that in order. I'm not going to skip anything because it really sucks if what you skip actually ended up being the thing you needed. So 126 is 1 times 126. Now it's 2 times something. Well, if you're not sure what that is, how do I figure that out? I just go 126 divided by 2 in my calculator. If it's a nice, friendly, natural number, I know that I found another factor. If I get some wonky decimal, then I know that 2 is not a factor and I wouldn't write 2 times anything, okay? Because it has to be natural numbers here. So 2 times 63, then I try 3 times 42. 3 times 42, I try 4, it doesn't work. I try 5, it doesn't work. 6 times 21 works. 7 times 18. So again, I just keep going 126 divided by 3, 126 divided by 4, 126 divided by 5. That's how I'm generating this, okay? There's nothing magical about what I'm doing right now. I try 8, 8 didn't work. I tried 9, 9 times 14. I tried 10, 10 didn't work. I tried 11, 11 didn't work. That's it. Now I'm gonna go over 144. Oh, you know what? I should explain that a little bit better, sorry. Let me just take that away for a second. So I tried 10, I tried 11, I tried 12, I tried 13, 13 didn't work either. Now I know I'm done. Okay, remember I told you I wanted you to go in order so that you don't miss anything. The great thing about this is once you hit the second column, like if I've tried 13 and 13 doesn't work, the next number to try is 14, but 14 sitting right there in the second column. So as soon as I reach where the second column is, I know I found all the factors and I know I haven't missed anything. Okay, so now we're gonna do the same thing for 144. Why don't you pause me and try it yourself and list them down. Okay, so this is what you should have gotten. We had 1 times 144, 2 times 72, 3 times 48, 4 times 36, 6 times 24, 8 times 18, 9 times 16, and 12 times 12. So now I have here all the factors of 126. I have here all the factors of 144. I now want the greatest common factor. So I need a factor that's the same in both piles, and it has to be as big as possible. That's what the greatest common factor would mean. So when I look at that, that is 18. Okay, so I can conclude that the greatest common factor between 126 and 144 is 18. Now, that's method number one. Method number two, we're going to use prime factorization. So I prime factorize 126. I break 126 down, and you could have started anywhere you want, but I just chose 9 times 14, and then I broke that down into 3 times 3, and the 14 into 7 times 2. So altogether, my prime factorization of 126 is 2 times 3 squared times 7. I take my 144 and I prime factorize it, so I broke it down into 12 times 12, and then each 12s I broke into 4 times 3, and then each 4s I broke into 2 times 2. And then I put it all together. That gives me 2 to the 4 times 3 squared. Okay, so I now have the prime factorization of 126 right here and the prime factorization of 144 right there. If I'm looking for the greatest common factor, I take a look at what's common to both piles. So there is a 2 common to both piles. There is only 1 2 common to both piles. Okay, in this guy has 1 2. This guy has 4 different 2s, but that means there's at least 1 2 common to both. This guy has 2 different 3s, and this guy also has 2 different 3s. So there are 2 3s common to both. 7 is not common to both, so I ignore the 7. What's common? 2 and 3 squared. So then I multiply 2 times 3 squared together, and I get 18. Okay, so that's another algebraic way, that's another way for you to show me your work on how you're going to get the greatest common factor. Now, if you have a Casio or a graphing calculator, or if you have a TI graphing calculator, your graphing calculators can also find these for you, and I've given you the keystrokes here. For Casio, you'd press Option, and then F6, F4, F6, F2, and then you put in your 2 numbers that you're looking for the greatest common factor for. Okay. The nice thing about Casio is all these keystrokes are opening up a menu. So once you have that menu opened up, you don't have to press them again to get back into that menu. That menu will stay there until you exit out of it or until you turn your calculator off. Then for TI, you go Math, and then you right click over to Number, and then it's option number 9, and you would input it. So make sure you see on your graphing calculators where your open brackets are, and then your comma. There has to be a comma in between your 2 numbers. They are very close to where your open brackets are. Okay. So go ahead, if you have a graphing calculator, play on it for a second. Make sure you can arrive at an answer of 18 for that as well. All right, now let's walk through how to find a least common multiple. So this question says, determine the least common multiple of 28, 42, and 63. Again, I'm going to show you 3 different ways. The first 2 are algebraic ways. So they're ways that you could show me your work. And then the last one will just be how to check it on your graphing calculator. Okay. So way 1, we want to go up in multiples of our highest one until we find a multiple that works for the other 2 as well. So until we find a number that happens to be a multiple of 28 and 42. So we're going to walk up in multiples of 63 until we find essentially a multiple of 63 that is also a multiple of 42 and also a multiple of 28. Okay, so 63 would be the first multiple we try, but I know right away if I go 63 divided by 28, I don't get a natural number. So 63 is not a multiple of 28. It's also not a multiple of 42, so 63 would not work. So then I go to my next multiple of 63. I'm choosing the higher one just because that will get me there quicker. So I'm going to go 63 times 2, and I'm going to try that. Okay, 63 times 2 is 126. When I try 126, I actually get that it doesn't work for 28, but it did work for 42. Okay, so 126 is a multiple of 42. How do I know that? Because I go 126 divided by 42, and I get a natural number. Okay. When I go 126 and I divide by 28, I don't get a natural number, so I know that 126 is not a multiple of 28. Okay, it has to work for all 3 in order for it to be the least common multiple. So I go to my next multiple of 63, which would be 63 times 3, which is 189. That does not work for either of them. Okay, so I just go 189 divided by 42, 189 divided by 28. So then I go to my next multiple of 63, which is 63 times 4, and 252, works for both of them. So when I go 252 divided by 42, I get a natural number. And when I go 252 divided by 28, I also get a natural number. Okay, so 252 is the least common multiple for those three numbers. Okay, if this is the way you want to show me your work, great. Personally, this feels a little laborious to me. It feels like it could take a long time. To me, there's a better way to do it, but it doesn't matter. Just because I say something's better doesn't mean you have to use it. You have to show me work. This is a perfectly acceptable way to show me your work if you want to, okay? The other way, though, is using prime factorization. So I'm going to just quickly do factor trees here and prime factorize these guys. You should pause me to practice that yourself. Okay, so 28 is 4 times 7. 4 is 2 times 2, so I get 2 squared times 7. 42, 6 times 7, and then my 6 breaks down into 2 times 3, and 63 is 9 times 7, and my 9 breaks down to 3 times 3. Now, when you're doing the least common multiple, you say, okay, you take one of every factor you see. It doesn't have to be common right now. You take one of every factor you see. So I see a 2, I see a 3, I see a 7. So right away, my least common multiple is going to start by saying 2 times 3 times 7. Okay? But then I take the highest exponent possible. So on a 2, well, let's look. I got an exponent of 2, I got an exponent of 1. So the highest exponent possible for a 2 is 2. On a 7, exponent 1, exponent 1, exponent 1. The highest exponent possible for 7 is 1. And then for 3, exponent 1, exponent 2. The highest exponent possible for 3 is 2. So 2 squared times 3 squared times 7. Now, this is cool. Put that in your calculator and see what you get. You get 252. To me, this is a much more efficient way of figuring out the least common multiple. Okay? And the nice thing about that is we've already talked about prime factorization. So it's a good review of stuff we did at the beginning of this lesson. Okay, again, to check it on a graphing calculator, for Casio, now you don't have to press all of these guys if you already have that menu open, right? You'll just notice that F3 says LCM. So you're good to go. And you can, Casios can input all three all at once. So you just go 28, 42, 63, and it will give you 252, okay? TIs can't do more than 2 numbers at the same time. So what you have to do is you have to walk through the process twice. The first thing you're gonna do is go math number 8 and go 28 and 42. Those are your first ones. That's gonna give you an answer of 84. So then you go 84 with your third number. So you'd have to go math number 8 again, go 84, 63, and then that will give you the 252. Okay. All right, good job, guys. Couple word problems here to end our day with. What is the side length of the smallest square that could be tiled with rectangles that measure 8 inches by 36 inches? Assume the rectangles cannot be cut. Sketch the square and the rectangle. So when you're reading this, you always want to look for key information, okay? The key phrase here is smallest square, okay? When you're looking for the smallest square, you're trying to think, okay, I need to make this dude as small as possible, but I'm going to make it using this rectangle. So I need to put these rectangles in here and make the smallest square possible. So the last couple of minutes, we've been talking about least common multiple and greatest common factor. Which one would be dealing with the smallest unit? Well, of course, it would be the least common multiple. So we want to find the least common multiple of 8 and 36. You go ahead and do that. Either do it through prime factorization or do it through listing the multiples. You will quickly find that it's 72. Okay? And that means that the smallest square we can form would be 72 by 72. And then it says draw the rectangles as well. So if you think about trying to put this rectangle in here, how many rectangles would fit this way? Well, if it's 8 high, I'd get 9 that fit down that way. And then with 36 wide, I'd get 2 that fit here and here. So that's how all those rectangles would fit into that square. Okay? Awesome. Okay, then the next guy, what is the side length of the largest square that could be used to tile a rectangle that measures 8 inches by 36 inches? Now, some of you may say, hey, that's the same question. No, you got to be careful with this. This is now, I'm using the square to tile a rectangle. In the previous example, I was using a rectangle to tile a square. Okay, so now the rectangle measures 8 inches by 36 inches, and I want the biggest square possible. Biggest, greatest common factor. I'm looking for the greatest common factor between 8 and 36. Okay, so go ahead and find me the greatest common factor between 8 and 36. And you will have told me that it's 4. So the biggest square that I can make is 4 by 4 squares in here. So now, how does that fit? Well, I'd have 2 this way, and I'd have 9 this way. So it would look something like that. Okay. So that's it for today. You guys can get started on some homework and some practice. If you have any questions, please make sure you connect with me. In the meantime, have a fantastic day. Take care, guys.